Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where we are discussing each and every chapters, their concepts and their PYQs, right? So today we are continuing with our topic of moving charges and magnetism chapter, and today we are going to discuss Ampere's law and solenoid. Also day after tomorrow there will be your KPL match number 3, where we are going to see a third mock test. Sunday morning I will be giving you a question paper. To get the question paper, I am receiving many queries from where I can get the question paper. Sir, how can I join the test series? It is absolutely free, and only thing that you have to do, you have to join our WhatsApp group. If you join our WhatsApp group in the morning, I will be giving you a 30 question set Sunday morning, that is, and in the evening I will be back with all the 30 answers. Okay, you will get the entire day to answer those questions, check your understanding, okay, do some research, find your mistakes. Once it is done, in the evening I will be back with clarification with all the details answered about the question paper. Now let's start with today's topic. What all we are going to discuss? We are going to start with Ampere's law, then we are going to discuss magnetic field due to a straight thick conductor. Okay, we have already learned straight conductor, but I made a mistake. I will be correcting that today. Then we will study about solenoid, and then we will learn about force between two parallel currents. Now let's start with Ampere's circuital law. Let's say we have a current. Okay, some current is passing in a region of space, some wires, not only one wire, there are multiple wires carrying current, and I want to find magnetic field around these three wires. Okay, so suppose the currents are I1, I2, I3, I4, I5. Do you find something similar to some laws that you have studied before to this diagram? In that case it was discrete charges, and instead of a normal surface it was a closed surface, right? Spherical surface. Yes, Gauss's law. In that case we have identified 1, 2, 3, 4 charges, different charges, and some charges are inside the surface, some charges are outside the surface. Similarly, here we are considering a surface, okay, with a closed boundary. Boundary must be closed. Okay, so boundary must be closed, and surface need not to be closed, obviously. Okay, and whatever current that is flowing into the surface, okay, and whatever the magnetic field on this point, say B, okay, and if I take a small portion of length, say dl, okay, if I take a small portion of length dl, and if I calculate this specific integral B dot dl, then we will get that equals to mu naught I. What is the meaning of I? I is here the enclosed current. So in this case I is basically equals to I1 plus I2 plus I3. It does not include any other current, I4, I5 or any other current that is outside this circle. Now remember that this magnetic, same as Gauss's law, this magnetic field is due to all the currents, but this integral is only due to this current which is included inside that surface. Okay, now what is the meaning of this integration? You might have wondered what is the meaning of this. So this means closed integration. Now what is closed integration? If you start from some point, okay, you go to some other point, various points, but if you end at the same point, okay, then that is called a closed path, right? So when you are you take small portion of it, you do some integration. If you take small portion from this path, and if you, after completing your journey, if you reach at the same point, then we say this is a closed integration. So in case of closed integration, upper limit and lower limit both are same, but it is along a defined path. Okay, even though starting point and ending point are same, and you have learned that it is supposed to be 0, if this is happening along a fixed path, it may not be 0. For example, in this case it is not 0. Okay, for any closed surface, closed path, along any closed path basically, okay, closed surface integration, closed path integration here, closed path integration basically gives you the total length of the path. Total length of the path, in this case the perimeter. Okay, so basically it gives you the perimeter. Okay, now you should remember that Ampere circuital law, similar to that of Gauss's law, is very much applicable when we are using symmetric surfaces. Okay, symmetric surfaces, symmetric curves. For example, in Gauss's law, most symmetric surface was a sphere. In Ampere's law, most symmetric surface is a circle. Okay, so Ampere's law we mostly apply using circle. You can apply any other surface, that does not matter as long as it is the closed path. Okay, but for our own convenience we use symmetrical surfaces, for example circle, or sometimes maybe square. Okay, where the integration is easier. Okay, but we are not doing any integration in this step, but this is the statement or formula for Ampere's law. You must remember that B dot dl should be equals to mu naught I. Here I is the enclosed current. Okay, now let us look into a problem based on Ampere's law. Okay, two identical current carrying coaxial loops. Okay, two ideal current carrying coaxial loops. Okay, carry current in I in opposite sense. Okay, so basically what is the meaning of that? One loop is this, another loop is this. One is carrying current I, another one is carrying current I. Okay, now simple Amperian loop passes through both of them once. So we are considering an Amperian loop which is passing through them only once. Okay, not twice, not thrice, only once they are passing through them. Now what is the magnetic field? They have given some options. So let us first apply Ampere's law. So in this case current is in this direction, current is in this direction for the other loop. Now what is the Ampere's law? Ampere's law says that any point, at any point B, B dot dl close integration should be equals to mu naught current enclosed. What is the current enclosed in this case? I, suppose this is positive I, then this should be negative I, because this is an opposite direction. So the total current enclosed should be 0. Now total current enclosed is 0, that means mu naught 0 is 0. Now dl cannot be 0. This is a real loop, real path, so dl has a value, it is not 0, right? So only thing that is possibly 0 is E, same as our Gauss's law, right? If there is no charge enclosed inside, then it will be 0. So B should be 0. So the magnetic field is 0 everywhere. So only if you see the options, B vanishes everywhere on C. So B vanishes everywhere on C means B's value is 0 everywhere on C. Okay, simple problem. So basic concepts of Ampere's law. This is also a KCET problem. Now magnetic field due to a thick conductor. So we have already done due to a thin conductor. Okay, I made a mistake yesterday. So today I will be correcting that. Suppose I have a wire carrying current I want to find say magnetic field. I want to find magnetic field at this point B, P, say BP. Now to form that, what we have to do, we have to construct a Amperian loop. Yesterday I said it can be solved using Ampere's law, it can be solved using Biot-Savart's law as well. Today I am using Ampere's law. So what we have to do, we have to construct a circle. I cannot draw the entire full circle in this board, but what I can do, I can calculate the magnetic field. Now we know that B dot dl close integral is equals to mu naught I. That is the Ampere's law, right? Now what we will do, we will apply this formula and calculate it. So B is, because of spherical symmetry, all the points on this circle from the wire will be equidistant. So equidistant means magnetic field will be constant magnitude of the magnetic field. So magnetic field will come out of the integration. Now dl, what I told about dl? dl is basically the perimeter. Now in this case we are constructing a circle, so dl will be 2 pi r mu naught I, or we can find the final value as mu naught by 2 pi I by r. Now yesterday I by mistake I said the value is I square, but it is not I square, it is only r square, but it is only r. Okay, it is not r square. So do correct your notes, do correct your understanding that it is only I by r. You should remember mu naught by 2 pi I by r. Okay, now what is the value for a thick conductor? Now instead of thin conductor like that, if we have a thick conductor, okay, we have a thick conductor, say again infinite length, but it is not thin, and for any point outside the wire, this is the formula. Any point outside the wire, you can close your eyes and you can use this formula. Okay, this is the outside. But what to do for inside? Okay, now the total current through the wire is obviously I. So what we have to do? We have to find the current density. Current density, to calculate the current density, what we have to do? We have to take the total surface area. Suppose this radius is capital R. Okay, the radius of the wire, say capital R, right? So in that case, the surface area will be pi r square. So the current density is I by A, that is I by pi r square. This is the current density. Now suppose I want to find magnetic field inside the wire at a radius smaller than r, say small r. Okay, here small r is obviously less than capital R. I want to find the magnetic field here. Magnetic field here. Now what we will do? So to find the magnetic field, starting equation is obviously the same. Okay, only thing here is that this I is no longer the total I, but it is the reduced I. So what is the value of reduced I? So reduced I will be, so first of all let me write the equation for this was for outside. Now this is for inside. Okay, obviously the initial stage I can obviously say the B is symmetrical, because this is also a circle. This is also a circle, right? So I can simply say this is B is symmetrical along the surface. So B can be taken out of the integration, and all similar to that previous problem where we have taken dl as 2 pi r, here also we can take the integration as 2 pi r. So most cases, if nothing is mentioned, you take that as circle and you write this as 2 pi r, right? Remember that when we are doing Gauss's law, in case of Gauss's law, we have taken E times 4 pi r square, right? Because that was the surface area of a sphere. Similar to that, in this case we will take B times 2 pi r, right? Now mu naught I is no longer this total current I, but it is current density times the surface area of this. So say the surface area of this is A dash, so J times A dash. This is the new current. Okay, this is the new current. Now what is J? J is I by pi r square obviously. And what is A dash? A dash is pi small r square, right? So pi cancels. Now if you write this value here, B times 2 pi r, 1 r will cancel from left hand side, 1 r will cancel from right hand side also, so 1 r will be still left. So B is basically mu naught by 2 pi, okay, I by I r divided by r square. Okay, so in this case B is directly proportional to r. Inside the wire B is proportional to r, outside the wire B is proportional to 1 by r. Okay, so if you plot the graph, of r versus let me plot the graph, let me make some space. If you plot the graph of magnetic field B versus distance r, okay, so till it is inside this wire, okay, it will increase linearly because R is proportional to R, so it will increase linearly till it reaches the surface. Okay, so at the surface of the wire, the magnetic field will be maximum, and then it will start reducing. Okay, because it is now proportional to 1 by R. So this is the graph for B versus R, very important graph. Okay, you have to understand this concept so that in exam, if something similar comes, then you should be able to answer that. Okay, now let us move and solve the homework problem of yesterday. A circular coil of wire of radius R has N turns and carries a current I. The magnetic induction B at the point on the axis of the coil at the distance 3R. So what was the problem? So we have a circular coil. Now one thing to be noted, that it will be root 3 times R, not 3R whole root. Okay, so in my problem yesterday, I think by mistake it was given as this. Okay, but this is incorrect. It will be only this. It will be only this. Okay, now what they have asked you to find the magnetic field at some point. This is the distance x equals to root 3 R. So you have to find the magnetic field here. Now if you remember the formula, what was the formula? B equals to mu naught by mu naught capital R square divided by 2 times x square plus R square to the power 3 by 2, right? So this was the formula. Now in this case, it is mentioned that the radius itself is small r. Okay, so what we have to do, we have to, instead of writing capital R, we will be writing small r square divided by 2 times, now x is given as root 3r. So root 3r, x is root 3r. So x square will be 3r, right? So just put 3r square plus r square, okay, to the power 3 by 2. So what is this value? 3r square plus r square, 4r square. So B will be mu naught small r square divided by 2, 4r square to the power 3 by 2. Now what is the meaning of 3 by 2? 3 by 2, so anything, suppose I have a to the power 3 by 2. I can write this as a to the power half to the power cube, right? Indices multiply. So I can write them like this. Now what is the meaning of to the power half? To the power half means nothing but square root, right? This is the main thing in this problem. Only thing you need to remember the formula and you need to remember this, nothing else. So basically, first of all, what you have to do, mu naught by r square divided by 2 square root of 4r square to the power 3, okay, or mu naught by r square divided by 2 times 4r square whole root means 2r to the power cube, okay. So it will be mu naught r square divided by 2 times 2 cube means 8 r cube, okay. So it will mu naught r square divided by 16 r cube, okay. So this is the magnetic field due to the coil at a distance, given distance. So the correct option is option A. Okay, little bit lengthy problem, but very simple, straightforward problem. Even though the mathematics is little long, but it is a straightforward problem, and if you practice such problems, it will be easier for you. Now this is a very straightforward question. Magnetic field at the origin due to a current carrying element dl placed at the point at vector position is r. So what is the, basically this is the other form of Biot-Savart's law I discussed yesterday. So when you are using r vector in the numerator, then there should be a cube in the denominator. Okay, if you are using only scalar form, then there should be r square. If it is you are using vector form with r vector, r cube should be there. If you are using r cap, then there should be r square. Okay, so r cap will be r square and r vector should be r cube. Now also we need to remember that it is dl cross r, not r cross dl. Okay, so dl cross r, mu naught by 4 pi obviously, and since you are writing r vector in the numerator, it should be r cube in the denominator, right? So no way it should be square and no way it should be r cross dl. Okay, now let's move on. Solenoid. What is a solenoid? First let us understand, you may have studied that in your class 10th, that solenoid is basically a tube where we round up some wires on top of that. Basically these are all insulating wires. Okay, now when we are considering this solenoid, what is the magnetic field near the center, in between the ends? Okay, the magnetic field in between the end is given by B equals to mu naught Ni. In this case, the small n represents the number of turns per unit length. Okay, number of turns per unit length. That means if you consider number of turns per unit length, say say length is 1 meter. When the length is 1 meter, whatever is the turn in that, that should be the total number of number of turns per unit length, right? So whatever number of turns here, that is the number of turns per unit length. It does not matter total number of turns how much is there. It only matters the number of turns per unit length. Okay, maybe you have only 20 turns, but the length is very small, so number of turns per unit length will be very, very high, right? So don't need to worry, right? And what else? Mu naught is obviously constant, I is the current. A solenoid of length 50 centimeter having 100 turns carries a current of 2.5 ampere. The magnetic field at one end of the solenoid is. Very interesting problem. Now they have given you 50 centimeter wire, so 50 centimeter length, so 50 centimeter length and 100 turns. So 50 centimeter length means 0.5 meter length and number of turns is 100 in that. Okay, so for 1 meter length, what is the number of turns? For 1 meter length, number of turns should be 100 divided by 0.5. In this case the formula is very important. Okay, only thing you need to remember is the formula and how you can apply the formula. Okay, otherwise this is very simple, straightforward. Now number of turns is 200. Now you should also remember that the formula that I gave you is basically for magnetic field near the center of the solenoid. Now here they have asked you to find the magnetic field at the one of the end. So to find one of the end, what we have to do, we have to construct one more solenoid. Okay, and if we have a solenoid of double length, say, okay, in that case total magnetic field will be half of that of this, right? So total length we have considered a double solenoid, so a magnetic field would have been half of that if only one is present, right? So here it will be double, but if only one is present, it will be half of that. So what was the magnetic field formula? Mu naught Ni, but half, because we are finding at one end. You should remember that whenever you are finding at middle, only mu naught Ni. Whenever you are finding any one of the end, it will be mu naught Ni divided by 2. Okay. Now what is the value of mu naught? One more important thing, we know that mu naught by 4 pi is basically 10 to the power of minus 7, right? So mu naught should be equals to 4 pi times 10 to the power of minus 7, right? So mu naught is 4 times pi is 3.14 times n we have calculated 200, and I is given 2.5 ampere divided by 2. So 2 cancels, one of the 2 cancels, and 10 to the power of minus 7 obviously. Okay, 10 to the power of minus 7. 4 pi 10 to the power minus 7, 4 pi 10 to the power of minus 7. Right? Now, 2 into 2.5 is 5. 5 times 200 times 3.14 times 10 to the power of minus 7. Now, 5 times 200 is 1000. 1000 means 10 to the power of 3. So, 10 to the power of 3 and 10 to the power of minus 7. So, it will be 3.14 times 10 to the power of minus 4. Now, everything is in SI. So, magnetic field unit is Tesla. So, it will be Tesla. Now, what is the value? So, correct value is option B. Should be careful while solving this problem. So, there is only one trick in this problem, that because it is one of the end, it will be half of the normal value. Okay. Now, force between two parallel currents. So, what is the meaning of parallel currents? We have two wires, say 1 and 2. Okay, current through this is IA, current through this is IB. Okay, the distance between them is small d, and suppose we are considering a length L. Okay, now this wire number 1 will produce a magnetic field where wire 2 is located. Similarly, this wire 2 will produce a magnetic field where wire 1 is located. And now they will interact with each other, and they will apply some force on each other. Okay, so they will apply some force on each other. Now, what is the value of the force? We know that moving charges passing through a magnetic field are experiencing some force called Lorentz force. Okay, so that force between two wires can be expressed using this formula. Okay, mu naught by 4 pi 2 IA IB d times L. Okay, now also if this wire, okay, pushes it with some force F on 1 due to 2, then this wire will apply some force on this F2 on 1. Okay, now also because Newton's third law is also applicable here, these two forces should be equal and opposite. Okay, if this is pushing it on this direction, this should be pushing it in the opposite direction. Also, one more important thing is that there is another quantity called force per unit length. This is basically F divided by L. Okay, because these two wires are very long, infinitely long, so the length has no meaning. So, we can calculate this as mu naught by 4 pi IA IB divided by 2 IA IB, because we have written 4 pi divided by d. And this is actually coming from the expression of magnetic field due to one single wire. If you want to do derivation, you can go and check your book. It is there in that, and it is also important for your board exam, PU board exam. Now, what will happen if I make IA equals to IB equals to 1 ampere and D equals to 1 meter? Okay, if you apply these two values, you will get that this force is nothing but mu naught by 2 pi. Mu naught by 2 pi, mu naught by 4 pi is 10 to the power of minus 7. So, mu naught by 2 pi is basically 10 to the 2 times 10 to the power of minus 7, right? And since it is a force, it should be Newton, right? Newton per meter actually. Okay, Newton per meter, but we will define it such that now we can define ampere. We can define ampere from this. Okay, ampere, because most of our life is based on mechanics. Okay, where we are applying force, we are measuring something, we are measuring acceleration. So whenever we can, we are trying to define everything in terms of our mechanics. Now, current electricity is completely different branch where mechanics is not very directly applicable, especially for current. So, how can we establish something with current? To define ampere, what we have done, we have taken this expression. Okay, the ampere is the value of that steady current, okay, which when maintained in each of the two very long straight wire, okay, of negligible cross section and placed 1 meter apart in vacuum, would produce each of these conductors a force equal to 2 times 10 to the power of minus 7 newtons per meter of length, okay. So this is the definition of ampere, also very important. But why I am discussing it, that sometimes they might ask you what is the force between two conductors kept at a distance 1 meter, okay, and 1 ampere current is passing through both of them. So in that case you don't need to do any mathematics, you can simply find 2 times 10 to the power of minus 7, right. So this value is important. Now one numerical here. Two parallel wires in free space are 10 centimeter apart and each carries a current of 10 ampere in the same direction. The force exerted by one wire on the other per unit length, okay. So here we have two wires, okay. Now two wires carrying current in the same direction produces repulsive forces, okay. So basically you can consider them as like charges. Two parallel wires carrying current in the opposite direction produces attractive forces, okay. Now what is the data? So the free space are 10 centimeter apart. So distance is 10 centimeter, that is 10 times 10 to the power of minus 2. As I always say, convert it into meter like this. Next is current, each of them carries a current 10 ampere. This is 10 ampere, this is 10 ampere, okay. Now the force experienced by them. Now what is the formula for force? Mu naught by 4 pi. If you see that there is, I have written like this so that you don't get confused. Force for unit length, okay, so small f. So Ia Ib divided by d. So I have written 4 pi here, 2 here. You can cancel this and get confused, but mu naught by 4 pi as a whole is easier to remember. That's why if you remember 2 IAIB by d, it will be, your life will be much easier, right? So mu naught by 4 pi is 10 to the power of minus 7. 2 times Ia is 10 centimeter, Ib is 10 centimeter, okay. Sorry, 10 amperes, not 10 centimeter. Distance is 10 centimeter, so it will be 10 times 10 to the power of minus 2. So one of the 10 will cancel. So it will be 20 times 10 to the power of 2 times 10 to the power of minus 7. So we can write this as 2 times 1 0 2 0, 3 zeros minus 10 to the power of 7. So minus 7 plus 3 minus 4, okay. So this is the force, Newton per meter, okay. 2 times 10 to the power of minus 4 Newton per meter, and it is repulsive in nature. So the correct answer is this, okay. You should remember, when the current is passing in the same direction, they are repulsive. When they are going on the opposite direction, they are attractive. So we have reached the end of this lecture. I have bring two very important homework, all from previous year questions. So pause the video, try to answer the question and mention the option, correct option in the option below. Mention homework 1, correct option, whatever it is, A, B, C, D, okay. Mention like that, homework 1. So use homework 1. So symbol for homework 1 is #1. Whatever answer correct, option, mention that option, okay. Now homework 2 is here. Also same way, pause the video, read the question and answer the question, and once you are done, you mention homework 2, correct option. We have a very detailed discussion on each chapter for KCET 2025 only. So we are doing everything possible for you so that you can score 60 out of 60 in upcoming KCET 2025 exam. And if you want, you can see every video in our playlist. The playlist is KCET 2025 Physics 100-day complete preparation strategy. Here we are, all the videos that I am doing will be available at one place, anytime, at any time of your free time. You can come and watch all the videos here, and you can have to join our WhatsApp channel to get the KPL 3 which is coming this Sunday. Don't forget to join our WhatsApp channel so that you get all the question papers. You will get the question paper for chemistry as well as physics in that WhatsApp channel. Soon mathematics series will also start. Don't worry, those who are waiting for mathematics series, it will also come very soon, okay. Now If you are watching this video for the first time, don't forget to subscribe to our YouTube channel and obviously join our WhatsApp group, and I thank you for watching this video.